And so I'm delighted to have him here today to talk to you about the history of Postgres. So please welcome Dr. Michael Stonebraker.
That you could rattle off all those companies. Also, I had back surgery 3 weeks ago, and I don't think I can yet stand for an hour, so I'm going to sit. As Ed mentioned, I won the Turing Award in 2015, largely for, or at least in part, for my contribution to Postgres, which I'm the original author of. And when you win the Turing Award, you get to write a paper that is published in CACM and give a corresponding talk. And the nice thing is that no one gets to review what you write or what you speak. So this is an unreviewed talk, which means I can say anything I want. And I did. So can we have the first slide? Okay, one other thing you need to know is that, and this is ancient history, most of you aren't this old, but in 1970, Ted Codd wrote a pioneering paper saying you guys, everybody should use tables to store their data. And his idea was all data should be stored in relations, simplest possible data structure, and accessed in a high-level language. Now, think SQL. These two ideas were absolutely revolutionary at the time. You guys think of it today as, you know, ho-hum. Everybody does this, but it was revolutionary at the time. And during the 70s, there was a huge controversy over whether you could build a relational database system that would actually work. And so it was an obvious research idea to embody Ted Codd's ideas. And there were two database systems that were full function that were written in the 70s. One of them called System R that came from IBM, turned into DB2. And one of them was INGRES that came from Berkeley, got commercialized in 1980. And they were two working prototypes that embodied Ted Codd's ideas. And with that, next slide. A subtitle of this could be Where Postgres Came From. Oh, thank you. Where Postgres Came From. The official title was The Land Sharks Are on the Squawk Box, or Why Riding a Bicycle Across America and Building Postgres Have a Lot in Common. So we started in the summer of 1993. Illustra, which was the commercial version of Postgres at the time, was down to fumes. We were out of money. And it fell to me to solicit more capital from our venture capital backers, who I affectionately call the land sharks. The only problem was I was at a family event at my brother's fishing cabin, which you see here on the slide, in rural Maine. This is in the 90s before cell phones existed. So I'm negotiating with the land sharks, and I have a rotary phone on the wall. The cord is stretched into the bathroom where I'm talking to the VCs, who of course on their Polycom in Menlo Park, California, which I affectionately call the Squawk Box. So the land sharks are on the Squawk Box, and I'm trying to get more capital. The conversation is depressingly familiar. They say more money, lower stock price. I say less money, higher stock price. Eventually, we reach a verbal handshake, and Illustra will live to fight another day. So as I said, this is going to be the tale of two different endeavors. One is a bicycle ride across America in the summer of 1988. The other is the development, commercialization of Postgres over a decade in the late 80s and early 90s. Both of these endeavors start off on a very high note, but as you can see, both of these are going to have a whole bunch of speed bumps that we'll go through in the course of this talk. So my wife Beth and I, here we are at the Anacortes ferry terminal. This is where you take the ferries to the San Juan Islands from across Puget Sound. This is our brand new tandem bicycle. Since I'm so big, it's a custom bike. We are very, this is on a high note. It doesn't faze us that we've never ridden a tandem before. The only reason my wife is willing to go with me is if we're welded together. Doesn't faze us that this bicycle has been ridden exactly once. It's brand new. It's still being debugged. It also doesn't faze us that we have an 18-month-old daughter who's going to be with us in this cross-country journey, who you'll meet in a second. And we have no idea how she's going to deal with life on the road. It also doesn't faze us that we've never been on a bicycle trip longer than 5 days, and it's obviously going to take a lot longer than that. It also doesn't faze us that we've never ridden high mountains like the ones directly in front of us. Here we are. We're about to head up the North Cascades Scenic Highway. Our destination will be Boston, some 3,500 bicycle miles away. Life is great. We're off on a great adventure. Well, here we are in Berkeley in 1984. I was the original architect of Ingress, and it got commercialized in 1980. 4 years later, commercial Ingress, is a 4-year-old company, has 10 programmers, and their code line is wildly better than the academic one that they started with. And it makes no sense for the academic project to continue prototyping on our code line. So we make the difficult decision to push the code off the cliff and start something new. So what will Postgres be? The first idea that had come up the year previously was something called abstract data types. How this came about was Ingress and SystemR were completely focused on business data processing. This is business, cash a check, all that stuff. And why was that true? Well, they were competing against the then popular ideas of the time, namely IMS, the database system from IBM, and the Codicil proposal from a collection of folks. So IMS was hierarchical, Codicil was network. We were the relational guys competing against the traditional vendors. So, and it would of course make perfect sense that that's what to focus on because that was the then big market. So starting around 1980 or so, there were a whole bunch of papers in the research community which says, this relational stuff is supposed to be the best thing since sliced bread. So I tried it on X. Computer-aided design, geographic information systems, library automation systems, ... There were about 40 papers that said, for a given X, we tried relational systems and they didn't work. And so to make them work, we added something to the relational model, times 40 with all different Ys. So this was clearly going to be death by 1,000 cuts. You had a clean, simple relational model, and the research community was proposing, polluting it with all kinds of stuff. So that was clearly a bad idea. So at the time, I was working with a research group led by Praveen Varaya. They wanted a geographic information system. And we were writing it on Ingress. And here's a typical example. So suppose you have an employee, in this case, Sam Madden, my colleague. He has an age. And then we want to store a rectangle that corresponds to Sam. Let's say, for sake of this talk, that it's the rectangularized location of his house. It's the plot of his house in Newton, Massachusetts. So you can represent a rectangle by 4 points, the lower left-hand corner and the upper right-hand corner. So then if you're the zoning folks and somebody wants a zoning variance on a given plot of land, the rules in most community are that you have to have a public meeting and you have to invite all the people within a certain distance of the place that wants the variance. So you have a rectangle, and a certain distance from that rectangle is enlarge the rectangle to a bigger rectangle, and you need all the homeowners whose plots intersect that rectangle. So this is rectangle intersects rectangle. Very popular GIS query. Well, the middle of the slide has, in fact, how you say this in SQL. In a talk like this, I invariably get somebody who claims that answer is wrong. I assure you, this is a well-vetted talk. The answer is correct, but it's messy, not intuitive, hard to figure out that it's the right answer. And what's more, if any of you know about the Postgres optimizer, it's very difficult to optimize because it's all got one-sided greater than or less than predicates. So this is a mess. And so how can we make this simpler? Well, the problem is Ingress had data types, integers, floats, and character strings, and GIS doesn't want that. GIS wants points, lines, polygons, rectangles, and all that stuff. So why not teach a database system to have data types appropriate to the problem at hand? So in our application, we want 3 columns, not 6, and you simply want a location field with some representation for a box. Doesn't matter what it is, no one's going to get to look at it. So you get an internal representation for the box. Then you need operators appropriate to geographic stuff. In this case, I want overlaps. So the query that is easy and trivial to understand is I want the names of people whose location overlaps, make a box out of the thing that I want the predicate to be. So everybody can understand this, nice and easy. And so the queries get much simpler if you can have data types appropriate to your problem and not the ones that some guy in Berkeley decided business data processing wanted. So in general, what you want is user-defined data types, user-defined operators, user-defined functions, and the idea is very simple. All this requires is adding some functions written in, say, C to a database engine and having them called at the appropriate times. So the idea is very simple in theory. In practice, of course, the devil is in the details. So you need to be able to have new indexes. You need to be able to put these new types in conventional indexes like B trees. You need to be able to teach the query optimizer how to optimize queries like on the previous slide, ... So the devil's in the details, but it sure seems like a good idea. Well, the bicycle ride started at Anacortes. Here we are in day 3 in Winthrop, Washington. I'm here with the driver of our support car, Marianne, and our daughter, Leslie. It isn't obvious in this slide, but I can just barely stand up. Today has been the hardest day I've ever experienced. We started off in Devils Lake, Washington at 5 a.m., and we rode uphill for 50 miles. Along the way, we climbed 5,000 feet into the Cascades. So this was up, and yet more up. Along the way, it got cold. we put on every piece of bicycle clothing we had with us. And then it started to rain. We go on for a while, and then it started to snow. And of course, there's no snow tires on a bicycle. So finally, cold and wet and exhausted, we get to the top, which is the aptly named Rainy Pass. And here we are. After a brief downhill, we have to climb another 1,000 feet to the top of Washington Pass. And after this, there's a glorious downhill hanging onto the caliper brakes on our bicycle, thanking God we have a third drum brake in the back to slow us down. And we get to Winthrop. So I'm elated, mostly because there are lots of mountains in front of us, but we're over the first two. We proved we can do the mountains. Okay, back to Berkeley. Chris State wrote a pioneering paper on referential integrity. He wrote it in 1982. You guys should all read it if you haven't. Basically, it's what to do with foreign key, primary key constraints. So you've probably all seen this example. You have some employees with departments, ages, and salaries, and you have some departments with floors, square footage, and budget. And what you want to do is look at the department field in the employee table. It's got a bunch of character strings, which are foreign keys, which point to primary keys in the other table. And so the problem is, what do you do if you delete the candy department? So mostly, what do you do with Art, who's in the candy department? He's now, the department field is now a dangling pointer. So what to do? So Chris State wrote this paper. Basically, he said, well, you have three options. If you delete the candy department, you can fire everybody in it. That will create a consistent database. You can take candy everywhere it appears and replace it by null, which is put all the employees in the null department. Or you can just refuse the delete because it's going to create an inconsistent database. There are three more actions on inserts, and these are clearly things you have to support in a database system. The problem is referential integrity is one of a whole bunch of these little rule systems. Second one that was popular in the 80s was triggers. So for instance, if you have a salary update to Sam and you want to make sure that Bill always makes the same amount of money as Sam, then you need a trigger that will propagate the update. Third thing is integrity constraints. Salaries have to be non-negative. So Ingress had these three things in them, and they were three different little rule systems. And first thing is, I hate rule systems. I just hate them with a passion. They were popularized by expert systems in the 80s, things like Prolog, things like Conniver, Planner. And the problem with rule systems is take two rules. One is make sure George is in the shoe department, no matter what. Second one is move everybody over 40 from shoe to candy. So here are two rules. So some update happens, and now you have to apply the rules. If you apply the first one, which is, let's say, move George to the toy department, then the first rule fires and puts him back in the shoe department. Then the second rule fires and moves him to the candy department. So George ends up in candy. If you do the rules in the other order, well, if George is over 40, then he gets moved to candy, and George will then get moved back to shoe. So in one application, he ends up in candy. In the other application, other order, he ends up in the toy department. So you get two different answers depending on the order in which you fire the rules. Database people hate this because it generates a database where you don't know what the answer is. And it's made worse by SQL being a set-oriented language, which is there's lots of tuples being updated by a single SQL command. and the net result is complete garbage. So first problem is rules don't have any nice semantics. Second problem is Prolog was the popular rule system at the time. The Japanese computing proposal said, write everything in Prolog. So a bunch of us would look at Prolog programs. And any of you who have ever looked at a 20-line Prolog program, I guarantee you can't figure out what it does. So rule systems are a mess, and they have terrible semantics. So my solution was to do something a little different. So SQL has an update command. So if you want to make sure Bill has the same salary as Sam, the update down in the middle of the slide is what does that. If you tag it with an always command, then the semantics are this command appears to be always running, and it will always make Bill have the same salary as Sam. Somewhat cleaner than an if-then-else rule system, so we are going to go with this and see where it led. Back to the bicycle ride. Here we are at day 15. We are at the top of Marias Pass in Montana, and we're at the Continental Divide. Beth and I are absolutely elated. All the endless climbs in the Cascades and the Rockies are now behind us. And more importantly, it's now downhill to Chicago. So life is good. We are really in an uptone mood. Back to Postgres. Well, the way database systems, you have to have crash recovery in any database system, because if you get a crash, you can't lose customers' data. Not allowed. So you guys all think of there's a database system, in your case Postgres, which is managing some data on the disk. But that's not what's really so. What's really so is that there's another database called the log, and the log is actually the statement of truth, because if you lose the data, you recover the data from the log. So there's two data stores with very different access engines. You have to do a thing called a write-ahead log. These databases have to be carefully synchronized, and I assure you the log code is ugly and complicated. What's more, it absolutely has to work, because if your log code fails and there's an important customer, then you can't recover the customer's database. You put your best engineers on an airplane to try and patch stuff back together. And if it's an important enough customer, you're on the front page of the New York Times. So log code is complicated, ugly, and has to work. That's a software engineering nightmare. So I said, why don't we do something different? Why don't we just use no overwrite storage, so that when you give Ed a 10% raise, instead of overwriting his data on the disk and then having to have a log to figure out how to back that out if you have to, why don't you just leave his old salary in the database, put a new record in the database with his new salary, keep them both, and therefore the log is simply intermixed with ordinary data, and you don't get all this ugly synchronization. Has a nice feature, because if you want to know what Ed's salary was yesterday, you just ask a historical query. We have the data in the database. Provides time travel in addition. Gives you something called a vacuum, which you guys probably all know about, which eventually garbage collects the old records. So this seemed like a really neat idea. Makes recovery wildly simpler. So of course the devil's in the details. You've got to make this perform well. No overwrite storage must be competitive against the traditional way of doing things. It can't be an order of magnitude slower. So the log has to be optimized for writing it a lot. The data has to be read optimized so you can read it a lot. And it's a tricky placement problem. So the Postgres Gameplan, circa 1984, bet on abstract data types, bet on rules using an always command, and bet on no overwrite storage. There's a bunch of other stuff in Postgres, but these were the important ideas. And we set off to build Postgres based on this stuff. Well, all of this so far has been uptone and we're on a high. The high doesn't last. Both of these endeavors hit speed bumps, one in North Dakota and then one in Berkeley. Oh, here we are. We get to North Dakota. And as you can see, it's a bleak and forlorn landscape. Beth and I joked at each other saying the state tree in North Dakota is the telephone pole. The worst thing about North Dakota is it looks like this. And so you ride east and up ahead 10 miles is a grain elevator. After an hour, you reach the grain elevator, which is in a little town. You ride through the little town in a minute or so. And up ahead, 10 miles away, is the next grain elevator. It is really a depressing landscape, and it all looks like this. But that isn't the biggest problem. The biggest problem is if you look at the flag on our bicycle, it's bent over backwards. The wind is howling. And in North Dakota, the wind always howls. And on a bicycle, what you expect to do is sit up straight in the saddle, and the wind blows you across the state at 17 or 18 miles an hour. Well, the wind was howling all right, but it was howling east to west. We were riding into gale force winds and struggling to make 7 miles an hour. So after a few days of this, we're really getting depressed, and it comes to a head in Drake, North Dakota, about halfway across the state. We were trying to get to a town called Harvey. That was our day's objective, and we weren't going to make it. We were too exhausted. And we ended up in Drake, and it's 250 miles to the Minnesota border against all these headwinds, and we're not sure how we're going to do it. Life is really not much fun. Well, in Berkeley, reality set in the next year. First of all, a unforced error was we chose to write Postgres in Lisp. Why did we do that? Well, Ingress was written in C. We didn't want to just do another system in C. C++ wasn't ready yet. Ada didn't look like it was going to make it. And the Japanese saying, write everything in Prolog. Let's try out, and all the AI guys were saying Lisp is terrific. So we tried writing Postgres in Lisp. It was a complete and utter disaster. Lisp is the slowest language on the planet. You can't possibly do system software in Lisp. So a lot of code goes over the cliff. The rest of it gets transliterated into C, and we're back to a conventional environment. The abstract data type system looks like it's going to work really well. How did I know that? It turns out that I was also working for Ingress at the time in the commercial Ingress. And commercial Ingress had just gotten done putting date and time as a data type into Ingress. And I immediately got a call from an important customer who said, you did date and time wrong. And I said, what in the world do you mean? We implemented the Gregorian calendar. That's what you're supposed to do. So March 15th minus February 15th is 28 days, except during leap year, except during double leap year. We did it right. And he said, that's not what I want. He had an application that dealt with bonds. And he said, in my world, bonds get the same amount of interest in every month, regardless of how long the month is. I want a calendar with 360 days divided into 12 equal length months. In my world, March 15th minus February 15th is 30 days. Thank you very much. So to get his semantics for time, he had to copy the by date, the cell date, out into an application, do subtraction out in user code, and then put the answer back. And it was a factor of 2 slower than if he could have done it in the database system. He said, all I want to do is override your definition of subtraction with what I want. But of course, you couldn't do that in Ingress, but that was child's play in Postgres. So Postgres was going to solve that particular user's problem. And so there are lots and lots of semantics for time. Postgres could do them all. Time travel has promise, but it's really tricky to tune. We're struggling with tuning it. And the always system doesn't work at all. So the problem is I set as the objective, you've got to be able to express all 6 of Chris Date's semantics for referential integrity using our always system, and I can't figure out how to do it. So a lot of code goes over the cliff, and we go back to exploring a conventional if-then rule system. So some things have promise, a lot of things just don't work. And for the next 4 years, the Wine Connoisseur and I spend all of our time figuring out how to fix Postgres. What to do about time travel, what to do about rules, how to figure out all the details of abstract data types. So think of the next 3 years as a long slog through the swamp, which the Wine Connoisseur and I, basically that was our life for 3 years. Well, the bad times don't last forever. We reach, life gets good again in both of these endeavors. What happened? Well, we left the bicycle ride in Drake, North Dakota with Beth and I being completely depressed, contemplating 250 miles against the wind. Here we are in Carrington, North Dakota the next afternoon. If you look at the flag on our bike, it's still bent over backwards. The wind is howling. That hasn't changed. But what's changed is my brother, David, who you see here in this picture, has shown up to ride with us for a week. He is a very strong rider. He's fresh. Marianne picked him up at the Minot, North Dakota airport, and he agreed to break the wind for us, like you see in the bicycle races. So we spent the day with him breaking the wind and Beth and I trying to ride 3 inches behind his rear wheel. That's much, much harder than you think. We made a couple of excursions into the wheat fields when we hit his wheel, but you know, faster, slower, trying to get the cadence right. We rode 82 miles to Carrington. It's now clear we will get out of North Dakota 3 inches behind my brother's wheel if necessary. Life is good again. So after the slog through the swamp, we got Postgres working well enough that we could contemplate building a commercial system. In the DBMS field at the time, the ultimate arbiter of good ideas is the commercial marketplace. You've got to get large customers to use your stuff, and they are the determiner of what's a good idea. So we wanted to make Postgres get used outside of the research community, and to do that, we had to have somebody to support it, and so we formed a commercial company called Illustra. And in my opinion, the best, if you have a better mousetrap, the best way to commercialize it is with a startup. There's a great book by Clayton Christensen called The Innovator's Dilemma. You should all read it every couple years. He's a professor at Harvard Business School. The basic premise is that if you're a big company, like say Oracle, and somebody comes along like Postgres with a better idea, it's almost impossible for you to morph from your traditional stuff to the new stuff without losing your customer base. So the big guys aren't interested in the new mousetraps, and so what you want to do is form a startup and threaten them. And that's exactly what we proposed to do. So we formed a commercial company. Any of you who've ever started a company, the first few months are an absolute high. You have money, you have the initial engineers, and you're off trying to make everything great. So we recruited a woman called Mom to be vice president of engineering. Her husband is a superb system programmer, I'll call the short one. EMP1 and the quiet one came over from the academic team, joined shortly thereafter by Triple Rock, with the tall shark as interim CEO and lead investor. We're off and running, convert the code from Quell to SQL, harden the code, improve performance, all the obvious things that a prototype didn't do. Life is great. So life is great on both of these endeavors, and it continues great for the bicycle ride. We get out of North Dakota, we go across Minnesota, my brother finally disappears. We go across Wisconsin, we go across, and we arrive in Ludington, Michigan, having just wheeled Boston bound off of the Lake Michigan ferry. Life is good, we are still pedaling. It's now less than 1,000 miles to Boston. It looks like we're gonna make it. So, in commercial Postgres, we are named Illustra after a couple of naming miscues. First thing you need to do as a commercial enterprise is get the first few lighthouse customers. We got the first few customers. We raised some more money. Remember slide 1. We hired a real management team, especially a person Uptone, who was the Frank Day of commercial Postgres. He was the marketing guy. The future is looking up. All we have to do is get some more customers. Well, the good times don't last for either endeavor, as you might expect. What happens? Well, we're lulled into complacence by the fact that the upper Midwest, Michigan, and Ohio are flat. It's easy riding, and we get to the Allegheny Mountains, and all of a sudden, it's more hills. The Allegheny Mountains are really horrible. It's up and down the same 500 feet over and over and over again. So we get to a place called Ellicottville, New York, and Beth and I are exhausted. We've been on the road for 49 days. And while Beth is putting Leslie to bed, I go and ask the innkeeper a very simple question. How do we get to Albany without riding all these hills? So life is really a challenge. Well, reality really sets in badly for Illustra. So we got the first few customers, and they're happy to either write their own abstract data types or use ours. And so we had written a geographic type library. It worked great. And the first few customers said, great, I'll use your type library. But then the next round of less adventuresome customers looked at our type library and said, I don't want your type library. I want the geographic types from the big geographic app vendors, people like ArcInfo and MapInfo. So app vendors, customers wanted ADTs from the big app vendors. So of course, dutifully, we made the pilgrimage to Redlands, California to talk to Jack Dangerman, who's the CEO of ArcInfo, and we said, we have this great proposal for you. You want to take all your geographic types, stick them in our database system. You'll get queries, you'll get crash recovery, you'll get all this neat, you get multi-user, you'll get updates, you get all this wonderful stuff. Jack Dangerman looked at us as if we were crazy and had a very simple question. How many users do you have? And we said, well, 15 or so. And he said, come back when you have 1,000. That presented us with a horrible catch-22. Our Illustra customers wanted Jack Dangerman's ADTs, and Jack Dangerman wanted more customers. And so we had a catch-22. And we're sitting there looking at each other saying, now what? Well, of course, things are not going very well, and our investors, of course, notice. And that causes something called a down round, which is we run out of money, and the investors say, well, things are not going well. We're not going to pay as much for your stock as we did last time. So that's what's called a down round. This is a fate worse than death, because what happens is It's very dilutive to sell stock at a lower value, of course. But worse than that, most of the investor agreements say that if you have a down round, you have to reprice previous rounds down to the new stock price, doubly dilutive. So the investors say, well, we're not going to, this is a down round, we'll put up more money, but at a lower price. The employees look at each other and said, you've just diluted us off the face of the earth, we're out of here, have a company. So that starts a horrible zero-sum game between the investors and the employees to recapitalize the entire company. That is just not much fun. So there's a catch-22 to deal with, and then there's the investors, and that's another horrible problem. So life is not looking good. So, of course, the bad times don't end up lasting in either endeavor. So what happens, we left the bike ride in Ellicottville, New York, with me saying, how do you get to Albany without climbing hills? The innkeeper had a great suggestion, which Robert Fulton 2 centuries ago knew very clearly. He said, ride straight north to the Erie Canal and hang a right. And that's exactly what we did. The Mohawk Valley is nice and flat. You ride right straight through some very ugly Rust Belt cities, but there are no hills. So we cross the Hudson River, we get to Troy, New York, and now all we have to do is deal with what I call the last hill. In Orinda, California, there's the bottom of a road called Wildcat Canyon Road. If you're a bicycle enthusiast in Berkeley and you want to go ride in the East Bay, and you want to then get back to Berkeley, the way to do it is on Wildcat Canyon Road, which of course is a big hill. So at the bottom of that road, there's a big sign saying the last hill. So in our world, we are now up against the last hill. All we have to do is climb the Berkshires to Pittsfield, and then it'll be easy going to Boston. Now only 186 miles away. Well, God is on our side in a really big way. There was this catch-22, the down round, things are not going well, but then the internet takes off. So that was exactly the time that Bill Gates goes to Cornell, gets an internet demo, goes back to Microsoft and says, we have to do this stuff. The internet gets just huge buzz. So Uptone, our marketing guy, turns the company on a dime. We are no longer about abstract data types, pushing stuff into, pushing function into the database system. We are the database for cyberspace. And we get a lot of buzz. Database for cyberspace, put your images, put your text, put your geography, all this stuff you can put in our database system. The other guys can't do this stuff. Life, maybe we've turned the corner. So life is looking up, and it turns out the giant internet vendor at the time decides he needs a database system. This will be a company-making transaction if we can pull it off. So we get invited to the party to try and sell our stuff to the large internet vendor of the day. Maybe we've turned the corner. In the bicycle world, there isn't another challenge. In the company world, there's another huge challenge, which is we get invited to the party, the Netscape Party, and Netscape decides to do a bake-off. So we say, great, do it on images, text, geography, do it on the new stuff. And he says, no, I'm going to do it on business data processing. For any of you who know history, he said, we're going to do it on TPC-B, which is basically cash a check. How many checks can you cash a second? And this is straight business data processing data. The elephants are very good at it by now. And the problem is we've never made that a priority. So transaction processing, we do it, but it's not something we've ever optimized. So we are going to lose this benchmark, and we're going to lose it in a big way. And the short one and I look at each other and say, oh God, now what? So both of these tales end on a high note. Many of you might think we were headed to Boston, that we would simply ride down Boylston Street, which is right out there, and then try and find the Atlantic Ocean somewhere to dip our bicycle wheel into. We decided that was an insane thing to do, and instead opted to go to Wollaston Beach in Quincy, about 10 miles south of here. We drag our bike across the sand, dip the front wheel in the water, and we're done. We retreat to a beachside cafe. We drink a glass of champagne and say, now what? Well, serendipity strikes again for the company. So the benchmark and Netscape have been so threatening to the elephants. They say, oh my God, we have to deal with all of this newfangled kind of data. And so one of the big boys decides to buy us. And that is serendipity big time, because there's still this catch-22 thing on ADTs and customers. Well, they've got a lot of customers. Second thing is they have a high-speed transaction processing engine and we don't. So we set about combining the two systems. The investors get a liquidity event. Life is good, the future looks great. So both tales end well. So about now you're saying, why in the world would I tell you guys a bicycle story? So here's an algorithm if you want to ride across the United States. So until you get there, loop, get up in the morning, ride east, persevere and overcome whatever comes up. And I guarantee you that if you do this long enough, you will get to the Atlantic Ocean. So you guys are computer scientists, so you say, well, let's apply a little bit of abstraction. So if you have a goal, then get up in the morning, take an action, persevere, and do it long enough, and you'll probably reach your goal. So you guys all know what macros are, so let's turn this into a macro, which I'll call just make it happen. So why would anyone want to ride a bicycle across America? As you've probably figured out, it is long and it is very hard. The mountains in the west are not easy. Against the wind in North Dakota is not easy. There's periods of depression and elation and lots of monotony, which is basically a slog through the swamp. So why would anyone in their right mind want to do this? Well, here's the answer. If you look at my capsule resume, well, I have a PhD from the University of Michigan. More or less, to get a PhD, you got to take a whole bunch of courses, some of which are very hard. You've got to take prelims, which I failed the first time. You've got to take quals, which I passed. You've got to write a thesis. Your advisor doesn't like your thesis. This is basically make it happen for about 5 years, sometimes more. Well, then I took a job as an assistant professor at Berkeley. You have about 5 years to get tenure, which means prove that you're famous to all the other people around. And being an assistant professor is really hard. You have to learn how to teach. You got to learn how to supervise grad students. You got to write papers. If they get turned down, you get depressed. If they get accepted, it's great. Basically, it's make it happen for another 5 years. So bicycle ride is some more make it happen for 2 months. There's an obvious conclusion to be drawn. I'm clearly goal-oriented. I like this kind of stuff, or I wouldn't do it. So why do I ride across the United States? Well, the answer's on this slide. You look at Postgres and you say, oh my God, Postgres is have a good idea. and then make it happen for about 5 years to build a prototype that works, start a company, hire superb implementers, hire execs, and then make it happen for another 5 years. So basically, building Postgres is have a good idea and then make it happen for a decade. So why would anyone in their right mind want to do this? It is long, it's hard. There's lots of bad times, there's good times. Well, I think you've probably figured it out by now. I'm drawn to make it happen, and I look for these kind of challenges. So here's some final thoughts. My personal thought on good ideas. Everybody asks me, how did you come up with the ideas in Postgres? Well, I've never had any good ideas by communing with nature on the mountaintop. Instead, I highly recommend hanging around very smart people like at MIT or Berkeley, talking to users, talking to more users, talking to yet more users. They'll be happy to tell you what they don't like about whatever they're currently doing, and your goal is then to fix it. I did a talk 4 years ago on where I thought the good ideas were. And so you can see my test of time talk in a conference called ICDE in 2015. So closing thoughts. Where does make it happen come from? I don't have any idea. Well, I do have some ideas, but you don't want to hear them because I don't know anything about psychology. It's way above my pay grade. But if you don't have make it happen, please don't get a PhD and don't become an assistant professor because they're too hard. What about serendipity? We wouldn't have got out of North Dakota without my brother. Illustra wouldn't have made it without the internet. It's often a really important factor, which of course is totally not under your control, as is anti-serendipity. I've been in environments where inadvertently one of the elephants crushes you, and then you close up shop and do something else. What's happening now? Well, our bicycle sits in our basement gathering dust. I refuse to sell it or throw it away. It has not been ridden since Wollaston Beach. I still love to take on physical challenges, most recently climbing all 48 4,000-foot mountains in New Hampshire. Illustra was successfully integrated into the Informix code base. Informix was sold to IBM. Informix version 9, which is the Illustra augmented system, is, to the best of my knowledge, still available. Go get it if you want to pay a lot of money for a database system. Postgres abstract data types have been added to most RD relational database systems. It's considered table stakes these days for systems. It's been wildly successful. However, the biggest impact of Postgres came out of left field, which is a bunch of people with no relationship to me, no relationship to Berkeley, picked up the academic Postgres code called Postgres 95 and have been shepherding the open source Berkeley system for the last 24 years. And that's the reason you guys are here in this room. And we all owe a big debt of gratitude to that cast of characters. This is open source development at its absolutely best. There is no company that is in charge of Postgres. It's a community effort. Postgres is open source. It's formed the starting point for a whole bunch of database startups, most notably Netezza and Greenplum. So if you look inside either of those systems, there's all the Postgres code with some extensions. I'm still building database systems. And since Postgres, I built a system called CStore, which turned into a commercial company called Vertica, as Ed noted. It's a column store for the data warehouse market. I built a thing called HStore, main memory, OLTP, blindingly fast system. Built a thing called SciDB, which is an array engine for the complex analytics market. Each of these took a decade, and counting. I could have used any one of these for the basis of this talk. There's nothing easy about building any database system, including Postgres. I need to have a shout out to the following 39 Berkeley students and staff. They wrote Postgres. You wouldn't be here today without them. They created Postgres 95. They're a very illustrious cast of characters. It turns out that Mike Olson is the chairman of the board of Cloudera, a internet platform vendor. Joey Hellerstein and Marty Hurst are on the faculty at Berkeley, and most of the others have had illustrious careers. So I owe these people a huge debt of gratitude. None of us would be here without them. None of this would be possible without incredibly talented system programmers. Postgres, the academic project, without people like EMP1, Triple Rock, and the Quiet One, we wouldn't have gotten Postgres to work well enough to commercialize. Most commercial companies are deeply indebted to a few very talented super programmers, and I'm in awe of people who have the skills, who can build complex code quickly and make it work. I'm in awe of startup executives, people like Uptone, who can turn a company on a dime when they see a market opportunity. In current life, I'm indebted to a man named Qball, who's in fact joining the Enterprise DB Board of Directors. He is a fabulous startup executive and has been the chief executive on multiple of my East Coast companies. And I'm indebted to the land sharks. Without their capital, we can't get any of this stuff done. And I'm told that Enterprise DB is getting refinanced by a collection of land sharks. Without them, we can't get anywhere. I'm, of course, incredibly indebted to my wife, Beth. Here we are 4 years ago in Cambridge in front of the MIT Stata building. Not only did she have to spend 2 months looking at my back riding across the United States, but she has to deal with my goal orientation, my penchant for starting companies. And I hope she realizes that she's the singular reason why I don't fall off a bunch of my own personal cliffs. To the right, you see Leslie, now all grown up, still blonde, and joined by my other daughter, Sandy, who didn't exist until after the bike ride. I'd like to close with a mention of Jim Gray. So Jim is about the smartest person I ever knew. He's a database researcher, worked for Tandem, worked for IBM, System R, worked for Microsoft. He was my colleague, mentor, sounding board critic, my friend. He was lost at sea about 10 years ago. And I think I speak for the entire database research community when I say, Jim, we miss you every day. Thank you very much. That's the end of the talk.